Okay, we're going to get started. First of all, welcome to the 2025 APS Colloquium. We're We're really excited to see everybody here. So thank you for coming, and we have an incredible lineup this semester. So with that, it is my honor to introduce our speaker and colleague today, Professor Jack Burns. Professor Burns is Professor Emeritus here in APS, and he's also the Vice President Emeritus for Academic Affairs and Research. He served on NASA's Advisory Council, both the subcommittee and the advisory committee, and he is a Senior Vice President and Fellow of AAS and is now on the Board of Trustees there. He's an incredible advocate for our field and an even more exceptional scientist. So with that, please welcome Professor Jack Burns.
Thanks so much, Shannon. It's great to be here and to kick off this semester's Colloquium series. Today what I want to do is I want to tell you a story. Okay, it's kind of an adventure story. It's a little bit of a personal story as well. And it starts 40 years ago, 1984, when a small group of colleagues and I wrote a first couple of papers with the scientific justification for doing radio astronomy on the moon. Over 4 decades in which we presented many such papers, many talks, many white papers to decadal surveys. Finally, last February, we saw our first radio telescope land on the moon. So it's been an exercise in persistence and nothing else. Now, having said that, it landed sort of on the moon, okay? So it wasn't a smooth landing, but the good news is we were able to get some data, and I'm going to tell you about that data today. I'm going to tell you about the results. We just finishing up a paper on that now to submit to the APJ. But I'm also going to tell you, and that first mission, the radio telescope was called ROLSES. But the adventure story is continuing because over the next few years, we have 3 more radio telescopes on 3 more commercial landers that are going to the moon, including this lander that you see here. This is the latest one to be announced by NASA just before the holidays that will land our ROLSES-2 radio telescope. This is Firefly Aerospace. They call us their Blue Ghost lander number 3, and you can see some of our antennas, our monopole antennas, out the side. Now, we're not going alone, though, to the moon, because Paul is going along with us here. He has an instrument called Lunar Vice as well. I'm sure he wouldn't mind saying a few words about it later on what that's going to be as well. So I'm going to talk with you about these other missions, what their goals are. Then I'm going to turn to a NASA-funded study that we're doing right now on designing a radio interferometer, a very large radio interferometer that's the ultimate cosmology tool in 21 centimeter to do on the moon, and then also talk a bit about some work that we're doing in lunar surface telerobotics as well to support that. All right, so let's start right off with acknowledging the funder, NASA, for the last 20 plus years. And recently we've entitled our group the Network for Exploration in Space Science, funded by CERVI. You see our many collaborators, co-investigators, and in particular students. And speaking of students, our most recent group, this year's group, I wanted to acknowledge because a lot of their work that we're going to be talking about is important there. We have undergraduate students working on telerobotics, Xavier and Grant, and then our graduate students who are working more on the 21 centimeter cosmology side. Johnny, David, and Joshua, I think, are all here as well. You'll be hearing about some of their work as we progress. So let's start right off with the science. There's 2 science goals that we want to do with low frequency radio astronomy. The first, as I've already alluded to, is 21 centimeter cosmology. So if you look at this cartoon picture of the evolution of the universe, Big Bang over here, today's universe over here is logarithmic in time, And that tends to emphasize this unsampled, the last unsampled part of the early universe called the cosmic dark ages. And the dark ages begins with the CMB. At that point, this is the epoch of recombination. So the universe at this time is filled with neutral hydrogen. It's before the first stars and galaxies form. So the only way to be able to sample that part of the universe is using the hyperfine line of neutral hydrogen, the famous 21 centimeter line, which is highly redshifted so that it appears at frequencies at below 50 megahertz. And the Decadal Survey, the Astro2020 Decadal Survey, singled out the dark ages as the discovery area for this decade in cosmology. And so that is what we are pursuing. There are two ways in the radio, in the low frequency radio, to investigate the dark ages of the early universe. And those are shown here. This is from a paper about 1.5 years ago by Mondel and Barkana. And it illustrates at the top what's called the global signal or all sky signal. Okay? Think of this as the counterpart of COBE's microwave background black body spectrum that was seen in 1990, 1991. A single antenna, because the signal's all over the sky. A single antenna has in principle the sensitivity to be able to detect that global signal if you're in a really quiet location, you have minimized your systematics, and you've integrated long enough to be able to pull out the signal relative to the galaxy. And the signal that we're looking at here, this is brightness temperature measured against the CMB, which is a kind of backlight for this versus frequency. And the signal I'm referring to is this blue trough that you see here. So it's a large trough. Frequency, but also because of being a 21 centimeter line, it also samples redshift. So we're actually looking at the evolution of structure in the early universe as a function of redshift. Now, the interesting thing about the dark ages, again, no stars, no galaxies, so there's no compact astrophysical objects. In the standard lambda CDM cosmology model, this physics is extremely simple. This trough is produced basically by the fact that the CMB cools more slowly than the baryons do. And it produces ultimately this large trough. Now, the other way to sample is through the power spectrum using a radio interferometer, and I'll be talking more about it a little bit later. Think of the early universe and the structure forming in the early universe and looking at the overdensities. Take the Fourier transform of that overdensities, and then look at the amplitude, square it, that's basically a power, and plot it as a function of wave number in inverse megaparsecs over here. This is the power spectrum. So what it does is allows us to sample the evolution of structure in the early universe. What you're looking at, the different colors here represent different redshifts, and the wiggles that you see here are acoustic oscillations due to sound waves in the early universe. Now, once again, because this physics in the standard lambda CDM cosmology is so simple that the prediction is very solid, very little room for maneuvering, okay? So that if we look at either the power spectrum or the global signal is different than this prediction, that means something else is going on. New physics, okay? What could that new physics be? Well, there's been a whole series of papers which have been published about this. Physics that leads to an investigation of not just the presence of, but the nature of dark matter. So dark matter that may be decaying, warm versus cold dark matter, sterile neutrinos that people have speculated about, early dark energy, non-Gaussianity in the initial density perturbations, which is what usually is assumed here, and even imprints of gravitational waves that can reveal information about cosmic inflation that is not accessible. So it is a playground of new physics that we can investigate here, as well as testing the standard cosmological model. So you can see the excitement, you can see the reason that the Decadal Survey identified this time period as being a crucial part of understanding cosmology. The second science goal is with regard to exoplanets. And that is to measure magnetic fields associated with exoplanets. This is the only way that we know of being able to make a direct measure of the magnetic fields. And this comes from looking at magnetic fields associated with planets in our own solar system. All of the planets in our solar system also produce low-frequency radio emission. And it's due to a process called electron-cyclotron maser emission. So you get a burst of energy from the sun. Those electrons get trapped and accelerated in the magnetic fields. They spiral in the magnetic fields, produce cyclotron emission. And the cool thing about the cyclotron emission is that the frequency depends only on the magnitude of the magnetic field. So here we have a way, not only in our solar system, but more importantly, thinking about exoplanets, of being able to detect magnetic fields and to measure the strength of the magnetic field. Why is that interesting? Because, of course, in our own case of the Earth, the magnetic field is very important in protecting life as we know it. So for habitable planets in particular, this could be an interesting measure. We, in the design of our interferometers on the far side, we've looked at the nearest exoplanets going out to about 10 parsecs or so. We think we have enough sensitivity to be able to potentially measure those magnetic fields in the nearest several dozen or so of those systems. So that's something for the future. All right, where are we going to do these observations? Well, obviously, we're going to do them from the moon, okay? We wouldn't be here otherwise today. And the moon is interesting and enabling for the three reasons I put here very simply. First and foremost, it's uniquely radio quiet. This is a topo map of the moon, the far side of the moon. You're sitting on this part of the far side of the moon. You get 2,000 miles of rock that separates you from the Earth. It's quiet, okay? We know it's quiet because the Radio Astronomy Explorer satellite from NASA in the early 70s in orbit of the moon. This is the relative antenna temperature versus time. This, where it says noisy, was when the satellite was above the near side. Where it says quiet, where it's above the far side. So it's dramatically lower, and you can see the galaxy. The moon also lacks any significant ionosphere, global ionosphere. And that's especially in comparison to the Earth, where that's very limiting on the Earth, because on the Earth, the ionosphere both refracts as well as absorbs radiation, particularly below about 20 megahertz. It's very difficult to see any low-frequency emission. Finally, the third ingredient here, which is not as well appreciated, unless you're a radio astronomer and having done some of these ground-based experiments like EDGES, is that the conditions in the subsurface are very important, because the radio beams connect electromagnetically with the subsurface, with the dielectric material in the subsurface. Now, on the Earth, that's a problem, because that changes from day to day, night to night, because of soil moisture. That's not a problem on the moon, okay? The moon's pretty dry. It similarly connects, but it does not vary in time, and it's stable. So that has an advantage. That needs to be calibrated on the moon, but it's an advantage. So all of those make the moon very attractive. Now, I talked about going 40 years ago. But people had, even before Apollo, were talking about doing radio astronomy from the moon, okay? Let me show you just a brief clip from Arthur C. Clarke. You know Arthur C. Clarke, okay? 2001 Space Odyssey, futurist, great science fiction writer. 1963, he was on British television and said the following.
But on the moon, and particularly on the far side of the moon, shielded from the electronic racket of the Earth by 2,000 miles of rock, there's an ideal site for radio astronomy telescopes. And I think that in a few generations, almost all serious astronomy will be conducted either on the moon or in space.
He knew his stuff. He knew his stuff. Okay, it's been 2 generations, okay? It's been 2 generations. We're there. Yes, serious astronomy is being done from space. Hubble, James Webb, Chandra, TESS, you name it. Lots and lots of space, but not from the moon until now, okay? So that's finally being realized, that moving forward in that particular direction. So why? Why has it taken us so long? And the reason is very simple. We've lacked access to the moon since the end of Apollo in 1972, over 50 years, okay? Now, we had an opportunity, I had an opportunity to make that change, to help make that change, by serving on the presidential transition team 8 years ago. And here's a picture of our team at that point in time. I've been beating my head against a wall for many years, putting in Explorer proposals, different kinds of proposals to NASA about this kind of work that we were doing. Always would get these great reviews on the science. And then they say, you want to do this from the moon? Nah, that's too hard. There's no way to get to the moon, yada, 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 okay? So being on this transition team came in with the idea of it's time to get exploration going again. The moon is the obvious next step to be able to do that, then on the Mars eventually. And so two things were proposed out of our transition team to the then incoming administration. That administration accepted it and has continued through the Biden administration, and I believe will be continuing through this next Trump administration. Two aspects of the moon. One you're very familiar with is Artemis. Okay, that's the human return to the moon using the Space Launch System, the Orion, and the goal is to put the first woman and first person of color on the moon later this decade. Now, at the same time, we also proposed something that came to be known as the Commercial Lunar Payload Services. Thomas Zurbuchen, who was the Associate Administrator for Science, he was just coming in then, I really hit him up hard on this one. And he became a true believer, proposed it, and put that in play such that this is a peer review program where Paul and myself and others can apply to fly payloads on the moon. It's unique, it's a public-private partnership. What do we mean by that? Well, in this case, the landers are designed, built, and insured by individual companies, and they also arrange their own rocket flights, okay? And so what NASA does is then to buy payload space, that is buy a ride to the moon. NASA has become the anchor tenant, if you will, for this program. And that's what we got started about 5 years ago and are now beginning to see this work. So our first radio telescope I mentioned earlier, it was called ROLSES, and originally intended to look at the electron sheath near the surface of the moon, which gives it its name. This is what we had hoped it would look like on the moon. I put hope up there just a little bit. You see two of our 2.5 meter monopole antennas extended over here. These are what are called stacer antennas. These are hollow tube antennas that are spring loaded, so you just open the spring, pops right out. Very reliable, works every time. The brains of the operation, our spectrometer board here has a sort of classical analog front end, digital back end with an FPGA. A lot of heritage that we were able to draw on. This was built by Goddard Space Flight Center. My old friend and colleague, Bob McDowell, was the original PI. He's since retired. Nat Gopalswamy is the PI now, and we have a number of really great folks on the team. Here at CU, we've done most of our work in designing the data analysis software and doing the data analysis and science for this project. Had two bands, a low frequency band and a higher frequency band that went for 10 kilohertz up to 30 megahertz in total. Okay, the adventure begins, okay? So here we are in the fairing of the Falcon 9 rockets about a year ago, okay? And this lander was built by a small company, one of these CLPS vendors called Intuitive Machines in Houston. They have about 400 employees, all young folks that's in there. The average age of employees in that company was 25. Okay. I got to say, this reminds me of a story. My old friend Jack Schmidt, the Apollo 17 astronaut, would tell me all the time. He would ask me and audiences, do you know when I was training for Apollo in the 1960s, what's the average age of employees at NASA was at that time? And the answer was mid-20s. Okay. Do you know what it is today? Anybody want to take a guess what it is today? That's right, mid-50s. Okay. Now, what happens to us as we age, Fran? There's that, but there's also we become more risk averse, okay, more bureaucratic. And that is certainly how NASA has evolved. And we took that on, I must admit, also in our transition team with only limited success. But this young team that they had for Intuitive Machines was really impressive in the problem solving that had to be done in real time. There was a number of things that had to take place. They nicknamed the lander Odysseus, who in Greek mythology, of course, had a number of chores and difficulty in returning home after 20 years in fighting the Trojan War. This little guy, too, had a fight to get to the surface of the moon. You can see the housing of one of our antennas right up here, the ROLSES antenna, which is, of course, not deployed at this point. All right, I love this picture. It's taken just hours before launch because here's our destination. Look at that, the crescent moon, okay? Getting ready to launch. And I got to say, SpaceX is great. I'm not in love with Elon Musk, but they really are good. They really are good. They know how to launch. Here was our launch.
5, 4, 3, 2, 1, ignition, and liftoff. Go SpaceX, go IM-1 and the Odysseus lunar lander.
Vehicle pitching downrange.
Picture perfect launch. Everything worked great. So we get to orbit, and about 48 minutes later, the second stage releases us. And here we are, our lander on a translunar injection heading towards the moon. And as we took about a week to get to the moon in this particular trajectory, most everything worked pretty well. We had a few glitches along the way, star trackers and so forth misbehaving. But they were, again, all solved by the Intuitive Machines team. So it worked very well. But about 6,000, part of the adventure here, about 6,000 miles away from the moon, the Intuitive Machines control room gets a message from our instrument. And it says, hey, you're overheating. The spacecraft was not rotating at the rate, it rotates like a rotisserie, a rotisserie chicken, and you want to rotate it and get all sides nice and warm. Well, in this case, it wasn't doing quite what we were expecting. So one of the antennas overheated, and we got a signal from the electronics. It looked like one of our antennas deployed. Wasn't supposed to do that until we reached the moon. Well, Intuitive Machines, as it turns out, took regular selfies. And there we go. There's our antenna. You can see it popped out over here. Surprise, surprise, it's there. And so we took advantage of that opportunity. So we went to Intuitive Machines and said, hey guys, can we turn on our receiver? Let's see if it's working. And we did. And we got about 80 minutes worth of data. In fact, that turned out to be the best data that we got on the mission, given what happened when we eventually got to the moon. So so that was good. That was kind of funky, but actually something good happened in that way. Now, everything was going pretty well till we got into orbit of the moon, and then discovered that the laser navigation system wasn't working. Why was that? Well, it turns out that because of safety reasons, anything having to do with a laser, when it's initially installed in the fairing, has to be turned off. And so Intuitive Machines had to actually install at the last minute a switch to turn that off. Before launch, someone forgot to turn it back on. Okay, so we had no laser guidance. There was a backup system. Turned out to have a software issue. That didn't work. Our tertiary system that we had was just optical imaging, which was pretty crude. So we came in hot to the surface. In fact, it was really, once again, it was a heroic effort on the part of Intuitive Machines to actually make it to the surface. We came in hot with too much both vertical and some horizontal motion. And we see a picture here just after it landed. Whoops, this is our landing location. Sorry, I'm a little ahead of myself here. This is our landing location. Think of Shackleton as the south pole of the moon. We were about 10 degrees in the little crater Malaparte A. We are still to this date the closest of any craft that has landed to the South Pole so far, but that record will be broken soon. Here is a selfie picture taken just after landing, and you can see what happened. One of the legs broke, okay? You can see the landing leg over here, and then this has come apart over here. Oh, not good. Now, of course, at the time, we didn't know it. At the time, we're listening to all of this, you know, and the radio broadcast coming back and the live YouTube and everything that's coming back on this, and everything, you know, was okay until we landed on the moon, and then dead silence. Nothing. 1 minute goes by, 2 minutes go by, 5 minutes go by, finally a ping. A ping from the spacecraft, very weak, came back saying, "I'm here," you know. But we didn't know what kind of state it was in. We didn't know at that point in time until later that it had broken its leg and it tipped over, okay? And you can see the very last selfie is shown here. This is the spacecraft, and you see its orientation about 30 degrees with respect to the surface. And Steve Ultimus, who is the CEO of Intuitive Machines, is showing this at a press conference, okay? So, yeah, not great. One of the not so good things is the high gain antenna was looking into the dirt of the moon, okay? That's not great. That's one of the reasons we weren't getting communication. But we did have some patch antennas, which were secondary communication. We went to some of the large dishes on the Earth in Green Bank and in Australia, and were able to improve the signal. We had enough power that we were able to deploy all 4 of our antennas and to get some data. But it was very limited data and just a small amount of that data. But enough so we could write a paper. And here it is. A year later, this is the draft. This is the very latest draft. Joshua Hibbert is the PI, justifiably so. He sweat bullets over this thing, I can tell you. And the rest of the team, and we're calling this NASA's first radio telescope on the moon. A couple of things we're able to do with it. One is to look at terrestrial transmissions and kind of techno-signatures of the Earth as an exoplanet. And the second is we made a tentative detection of the galaxy, the first detection of the galaxy from the moon. So modest products, but still pretty good. Here's what the data looks like. Now, with these kind of antennas, we have really no spatial or angular resolution to speak of, but we have good spectral resolution. So this is our product. This is called a dynamic spectrum or a waterfall plot, frequency versus time. This is the data from in transit, the 80 minutes that I told you when the one antenna popped out. And this is data we took from the moon, only about 15 or 20 minutes worth of data there. All of these horizontal stripes that you're seeing over here, those are radio transmitters. We are able to verify this in 2 ways. Number one is that in looking at the time sequence data, those data are modified by ionospheric density perturbations, having sort of a classic time sequence look to them. And secondly, we also compared to data taken with the LWA at Owens Valley. You remember Greg Hallinan was here back in the fall and talked about the LWA. So we used some of that data and some good comparison between some of those lines. Now, why do the two look so different in transit and on the surface of the moon? Well, we think that has to do with the orientation. Johnny DeRigo Jones in our group worked on understanding the orientation of the Earth at these two time periods. And you can see they're quite different. These observations were taken at night. In the first case in transit, we were looking right at the north and south hemispheres. At night, a lot of radio transmitters. The second one over here, as it turns out, we're looking mainly at the Atlantic Ocean. Okay? So not as much and a different frequency distribution that we're seeing up over here. But as I said before, what is interesting is, in particular, these data that we're seeing from in transit. These are the best radio data that we've taken from the Earth over this bandwidth from 1 to 30 megahertz. And it does serve as kind of a template for what we might expect in doing a SETI experiment of exoplanets. So with this radio interferometer that I talked about a little while ago, to look at the magnetic fields, we can also look at potential signatures. And this is the kind of thing that you might find from an intelligent civilization. We're not sure if there's an intelligent civilization, but maybe from an intelligent civilization, that's what this might look like. So we have this template. The other thing, and here's where Joshua, I just can't give him enough praise, because this was really hard. We had to clean the data. We looked at the time sequence data that was available to us at this point. Really clean up, look for the quietest region, and after doing a lot of editing and working on these data, we found that we had about 5 minutes of really clean data on the surface of the moon. This is where this time sequence was available. And so what we did is we asked the question, can we see the galaxy? Okay, and that's really ambitious. Okay, 5 minutes a day to see the galaxy. And so what we're seeing from the instrument, the voltage is directly proportional to these instrumental characteristics plus the galaxy brightness. So what we did is, using a number of fairly sophisticated statistical techniques and nested sampling, what you're looking at here is a fit and the covariances for these instrumental parameters and the normalization of the galaxy, which is right in here. So this is what we expect, the dashed black line, based on previous observations that had been made by Novico and Brown. And we're finding, although the errors are pretty wide, there's a pretty good look that we have detected the galaxy. Why am I excited? Because we of course detected the galaxy a long time ago. This is looking at lower frequencies, 5 megahertz or so, but 5 minutes. This is pretty impressive. 5 minutes to be able to dig out the galaxy spectrum in light of all of these instrumental issues. So that's pretty encouraging. All right, the adventure continues. Okay, NASA has funded us to do a ROLSES-2, and that's going to fly in 2028. And we've already begun at Goddard the construction of the antenna, the spectrometer board. Here's the stacer antennas out in the field a few weeks before the holiday break. We've made a number of upgrades and improvements that you see over here, including more shielding, new internal cal sources, and now all 4 antennas will operate to allow us to have full Stokes polarization. So in total, here are the 4 missions. I've already talked about Intuitive Machines and ROLSES-1, ROLSES-2 on the Blue Ghost lander. The two other missions is one called LuSEE-Night, which will land next year on a Japanese iSpace Draper collaborative lander, single monopole that points directly up, mainly for sensing the plasma near the surface. And then this next one, which I want to talk a little bit more about, is called LuSEE-Night. This will be to the far side of the moon and our first 21 centimeter cosmology mission. Okay? And this is to land about a year from now. This is another look at it. This mission is led by my colleague Stuart Bale at UC Berkeley, and it's a collaboration between NASA and the Department of Energy that I helped to negotiate with the previous NASA administrator. This is the engineering design that you see here, the lander down below, our instrument box on top. Fairly simple altogether, except the secret sauce here is batteries. We're carrying 40 kilograms of batteries. That means we can operate at night, okay? So we'll be the first spacecraft to be able, US spacecraft to be able to do that, and that's where our most sensitive data is at night. And so that's very important. Most of the mass is in batteries. you hate to see that, but that was the option. The antennas are cross dipole antennas you can see on top. They're on a turntable, and we did this purposely because we have an ability to be able to rotate the antennas because there's a calibration source I'll tell you about that we're putting in orbit as well. That's very important to calibrate the antenna. Our landing spot, as it turns out that as the package grew and sort of the importance grew, NASA threw everything else off the lander. We're an all 21 centimeter cosmology lander, okay? We're the only experiment on board. So we're able to pick our own landing site, which we did. And it's near the anti-meridian on the far side, about 25 degrees south, a little bit cooler there than at the equator. Now, having said how great the moon is, and it is great, and the far side of the moon, it's still a difficult observation to make because we have to look through the galaxy. So very similar to the CMB, and the same level of sort of CMB polarization. What you're looking at here is brightness temperature against frequency, and here we're looking at two things. In red is one model of the 21 centimeter signal. This is weird looking here because we're plotting log versus linear. And then here is the galactic foreground. So unlike the CMB, the galactic foreground at these low frequencies is synchrotron, mainly from the galaxy, some extragalactic. Now, you all know synchrotron radiation is basically a power law. And so that, in principle, is kind of nice. Should be simple. Here's the difficulty. We're looking at that galactic foreground through a beam that has a lot of frequency dependence. Any antenna you design, any, has frequency dependence. And it's complicated because that antenna beam also couples to the spacecraft, it couples to the subsurface, so it becomes a complicated situation. Makes for a complicated signal, so you can't simply subtract it out, especially when you're looking at 4 to 6 orders of magnitude difference between the foreground and the signal that you're looking for. So this is the reason we convinced NASA to do two things. Well, along with our lander, they are flying a communication satellite, which we need to transmit the data back. Duh. It would be kind of dumb to just get there without a communication signal. But secondly is we also are flying a radio beacon. That Firefly Aerospace is also putting up a platform in orbit of the moon, and on board there will be a radio beacon transmitting a known waveform at certain intervals back to the spacecraft. The antenna turns underneath so we can map that antenna beam and attempt to calibrate and deconvolve the effect of the frequency dependence of the antenna from the signal that we're looking at, okay? So elements of this have been tried on the Earth using drones above arrays on the Earth with limited success. We have a simpler environment here, but still complicated. But we think this will be part of secret sauce. Now, having said this, there's a whole lot of software that is necessary in order to attempt to pull this out, and a lot of forward modeling, and I could spend an entire hour on this alone. Would you like me to spend the time? No, you would not like to spend an entire time. But my students would like to spend an entire hour because it's really good stuff. So I'm only going to flash up a couple of recent papers that they've been working on because I want to acknowledge the good work that Johnny DeRigo-Jones, Joshua Hibbard, and other members of our group have been working on. These are 2 papers on emulators, using also some neural network software to assist in doing fits of both the 21-centimeter signal and also the antenna beams. So really a lot of statistical analysis necessary, forward modeling, Bayesian forecasting to be able to do this right. All right, so I won't run out of time. I'm going to say, let's skip forward, okay? And what are we going to do next? The next thing is a radio interferometer. This is where we're heading, okay? And we're now in our second phase of funding from NIAC, the NASA Innovative Advanced Concepts Program, for a cosmological telescope that will have 100,000 dipoles, okay? So we're not being modest, okay? 100,000 dipoles. That's what it takes to see the power spectrum, though, at these frequencies. And the other thing that's kind of cool about this is working with a company called Lunar Resources in Houston. We've developed technology to extract metals from the regolith, or the soil of the moon, and turn those into antennas with advanced manufacturing techniques. And we've demonstrated those in the laboratory, and I'll show you a little bit of that. That's important because having to drag all that metal to the moon is extremely expensive. And so there's quite a cost savings associated with this. This is one of the reasons I think NASA also selected this project, because it accomplishes 2 things. One is working towards the science we want to do, and second, demonstrating the construction in situ of a scientific telescope on the moon. Here's our architecture. And this has evolved over time, but this is our latest version based on some recent numerical simulations that we have done. It's a hierarchical structure in which we have 80,000 of the dipoles are placed in the center of the array, very tightly packed within a diameter of about 4 kilometers. And this is what's necessary in order to really pull out that signal, as I'll show you in just a moment. And surrounded by, in this halo structure of antennas, this will be used to measure the foreground from the galaxy primarily. Now, switching to the smallest level and building back, each of the the cross dipole antennas you see there are being put into subarrays, 4x4 subarrays. The reason being that we can phase those subarrays and will reduce dramatically the number of correlations we have to do, and therefore the computations. And that's equivalent to each one of these subarrays to a dish antenna that's about 25 meters in diameter, has similar effective area to that. Each one of these subarrays then we pack into what we call an antenna cluster that's 6x6. This is done not for science reasons, it's done for practicality, because each one of these antenna clusters will have its own solar power station that we will also build and extract the silicon from the materials in the lunar soil to construct that. We then put these clusters, as you see up over here, into the core to make the entire array. So how did we come up with this design? Well, this was driven by the sensitivity. It's all about the sensitivity to be able to look at this. So this is just one of many such plots that we have done to demonstrate this. This was led by Johnny Pober at Brown University and one of his students. What you're looking at the power spectrum again as a function of K. In black is the result of our simulations with roughly 80,000 tightly packed antennas in the core. And then the models of the expected signals here. In blue is the standard lambda CDM cosmology. So no new physics in there, just standard. That's the hardest signal to see. But we still get 10 sigma here in terms of detection. If there is some added physics, here's a couple examples of parametric models with added additional cooling in orange and green. And you can see that the signal is enhanced, our ability to be able to look at that. So based upon that sensitivity need, this is what drove us to design the particular core halo structure that you are seeing there. All right? And we also modeled then specifically on the moon. We put the telescope on the moon. We looked at the beam, what's called the UV coverage. These are projected baselines on the moon. With 100,000 dipoles over 5 Earth days, not a surprise, it looks pretty darn good. We got a lot of baselines there, and it achieves better than 1% side lobes on the moon with no cleaning or anything associated with it. So that's pretty good. How about this in situ manufacturing? This is kind of cool. And the NIAC reviewers that we had about 6 months ago looking at our project looked at this and were pretty impressed. Put together by Lunar Resources. It's called molten regolith electrolysis. Those of you who know a little bit about electrolysis. Electrolysis requires a really high vacuum. Guess what we get for free on the moon, okay? A really high vacuum. So that's good. That helps with this. So my colleagues at Lunar Resources have built a reactor, and recently that reactor was placed in a vacuum chamber at the Kennedy Space Center and tested out, and we're able to manufacture some individual antennas which had very high conductivity. These were aluminum, made of aluminum, from the regolith material. So that bottom line is now that in terms of our requirements, that extracting silicon, aluminum, and magnesium is viable. This process now is at TRL6, this technical readiness level that NASA leads to talk about. We'll need 6 of these units, which will be about 4 metric tons that we will bring to the moon. Now you go, oh, 4 metric tons, that's a lot of stuff. The Starship, the Lunar Starship, is supposed to take 100 metric tons to the moon, okay, a single Starship. So, but with that, 4 metric tons, we can generate 45 metric tons of aluminum. So that's a pretty good trade of what we're going to be able to need there in a wire fabrication process. Let me show you a little video that we put together of this, kind of both an information and to advertise this a little bit. This
FarView is a technology concept for a next-generation astrophysics radio observatory that could be built on the moon's far side. The only radio-quiet place within the inner solar system to study the earliest stages of evolution of the universe. The Lunar Observatory would be built from Lunar Resources and constructed directly on the surface of the moon using space industrial equipment sent from Earth. The required materials would be extracted by Lunar Resources manufacturing technologies from the lunar regolith.
And this is the music you hear on the moon when you're doing
this. The truck rover then
this.
delivers the extracted raw materials to the construction site for the fabrication of antenna elements, solar cells, electrical transmission cables, and batteries. The observatory's antenna array and power grid could then be assembled directly onto the surface of the moon, utilizing Lunar Resources space manufacturing technologies and its partners' intelligent lunar rovers. FarView is planned to be a 14 by 14 kilometer observatory with 100,000 dipole antennas and could take less than 4 years to be constructed. The Lunar Observatory could explore the origins of the first structures in the universe, opening new windows into low-frequency radio astronomy, uncovering new physics, testing standard cosmological models, and enabling new discoveries in heliophysics and planetary science. FarView could be one of the most powerful radio observatories for learning about the formation of the earliest structures in our universe.
Woo! So as you could see in that video, that a very important part of the design is rovers that are teleoperated. That is, they're remotely operated by astronauts on the moon or operators from the Earth. So recognizing this years ago, about 15 years ago, we created here at CU a telerobotics laboratory that is run mainly by undergraduate students. This is the latest paper. In fact, we're just getting ready to resubmit, right, Xavier? We're almost done, ready to resubmit this to the journal. It's already gone through one round. And the idea being is one of the things that we were looking at here is we built our own rover called Armstrong. So it has an arm here. It's Armstrong. Okay. It's also Armstrong. You know. Okay, you get it. And pretty little sophisticated thing that we've put together over the years. I'll show you a little bit more about that. And then in the last couple of years, we built a virtual reality digital twin that we put inside the Unity game engine, so that this served as a way of being able to calibrate our instruments, to train operators, but also to do real-time problem solving in an environment where we can control gravity, soil conditions, and so forth, more so than what we could do otherwise. So let me tell you a little bit more about this and just mention two of the other members of our team, Katie McCutcheon and Alexis Muniz, were part of the team last year. They've moved on since then, but Katie did this video that I want to show you.
An essential role in the upcoming crewed missions to the moon. For example, the FarSide mission will utilize autonomous rovers to deploy antennas on the far side of the moon. We are investigating the applications of telerobotics for use on the lunar surface. Telerobotics is an area of robotics in which humans operate robots from a distance. We designed a simple rover that can be operated from a distance using virtual reality. Our rover, Armstrong, has a robotic arm that can pick up and rotate objects. Armstrong has a simple drivetrain that allows for motion forward and backwards, as well as rotation left and right. Armstrong receives commands from the user via a wireless gaming controller. Commands are processed by a small computer on Armstrong. Users are able to look around Armstrong's surroundings using an Oculus virtual reality headset. Armstrong's cameras rotate using servo motors to match the position of the Oculus headset. The operator's mission was to examine the antenna array and locate the misaligned antenna, and then attempt to realign this antenna. Operators perform the task in first-person view using the Oculus headset to see through Armstrong's cameras. The best way to approach this task is to approach the antenna so the gripper's jaws are perpendicular to the antenna. Then, close the gripper around the antenna body, and drag and rotate the antenna on the ground until the antenna is aligned with the printed outline. This technique was chosen to limit the likelihood of the antenna falling over. If the antenna was knocked over, we paused the experiment and reset the antenna. Due to system limitations, inaccuracies of up to 10 degrees misalignment were accepted. After successfully aligning the antenna assembly, participants removed the arm from the antenna and informed the experimenter that they were finished. Operators had 15 minutes to complete the task. After this, several surveys were completed to evaluate operator experience.
So we brought in 24 operators, that is, we recruited. We had to go through to IRB, the Institutional Review Board, to do this, and did an experiment in which half of the folks used only the real physical Armstrong to do the experiment, and the other half used first the digital twin and then the real Armstrong. And one of the questions we asked was what improvement, and you can see just one of the plots in the paper showing a dramatic improvement in using just the physical rover alone and the time to completion versus the time to completion with that training. So again, a fairly simple experiment, but one that was still kind of cool to do. And this, to our knowledge, is the first time anyone has proposed using a digital twin kind of environment for a planetary sciences rover. So we're looking at. With that, I think I am going to stop. I probably talked enough, and I will put up my summary and conclusions and be happy to take some questions. Thanks. The adventure continues.
Okay, are there questions for, okay.
Two quick questions. Number one, what about the impact of dust on your antenna? And secondly, what about looking at Uranus and Neptune? Because you showed their fairly low frequency, intensity compared with very intense Jupiter and Saturn. But we're going to have a spacecraft, we hope soon, before too long, priority of the planetary decadal, to go to Uranus and maybe Neptune. And because of that weird magnetic field tilting around, it would be fantastic to get a better measurement at Uranus. Also a calibration for your exoplanets.
So, Fran, I'll do the second one first because you're absolutely right. We've been thinking a lot about Uranus and Neptune as primary targets to be able to do both with a testbed array, which we want to build first before the full FarView, and even with LuSEE-Night, we're going to attempt to see if we can detect Uranus. That's going to be tough with a single antenna. Dust doesn't affect, of course, us at radio, so that's not a particular problem. What we are going to do in building FarView is we're going to drill down about 10 or 20 centimeters into the regolith and put our preamps down there. So that will shield us from cosmic rays, and also down at that level, the temperature is stable. So that's one of the things that we're going to attempt to work on.
Other questions? Because I have one. Could
Okay.
you comment a little bit on your on the Department of Energy collaboration? That was interesting that they have been contributing to NASA.
It was. So I'll tell you about a little bit of space politics here. So I mentioned to you I was on the transition team, and as a result of that, really got to know Jim Bridenstine, who became a NASA administrator, pretty well. And Jim was a great guy. We had dinner a number of times together and talked about all of the science you can do, and he fell in love with the dark ages of the moon. So we talked together about an experiment. You know, early on, just as CLPS was getting going and kind of running short on funds, and so he said, you know, I just had a meeting with the head of science in the Department of Energy. Why don't I call him up and talk to him, see if he's interested in partnering? And so that's how this came together. It was done from the top down. And so the Department of Energy is putting in about 15 million. NASA is putting in about 20 million for the experiment. The lander itself is about 100 million to be able to do. And so that's how that partnership came together. DOE is interested in this because this is in their science wheel well, because they're interested in dark matter and very frustrated that they have not been able to detect dark matter on the ground using the techniques that are available. Maybe this is an avenue to be able to do it. So that's where the science part of this comes in.
That's exciting. I didn't know if that was the battery you talked about. So that's exciting. I didn't know that the DOE was interested there.
Yeah.
All right, 1 and then 2.
Thanks for the talk, Jack. The science is really interesting, and I have a sort of a geopolitics question, maybe, or of ignorance. For FarView, you have to pick a 14 square kilometer place to put this thing down. Who gets to decide where that goes, and does everyone else have to agree? What if someone else comes along later? I mean, this would be an embarrassment of riches. What if someone comes along later and puts something that's radio noisy nearby?
Yeah.
What do you do?
Yeah, those are all great questions because these are ones that, you know, we are wrestling with right now. I'm on several panels, the ITU, the International Telecommunications Union. The IU has a new working group on the moon, both dark and quiet on the moon. So these are long-term issues. This is one of the reasons we want to get to the moon and do these things as quickly as possible too, before it does get polluted. but also looking at controls for the future. The good thing about the radio frequency band that we're working in is that it doesn't overlap at all with any of the communication bands, which are much higher frequency. But we've seen with the Starlink satellite recently that it leaks. It leaks at just the frequencies we're concerned about. So this is data from Starlink that was taken by the LOFAR radio telescope in the Netherlands. And what we're seeing here is radio emission between 56 and 66 megahertz. So we're getting pretty close to what we're looking at 1,300 Janskis, okay? That's blasting, okay? And that's from these Starlink satellites. Where's it coming from? It's not comms, it's leakage from the electronics, from the power supply. Starlink did nothing, apparently, to shield their instrument. A simple Faraday cage would have gone a long way. They didn't do any of that. They're in violation of the United States MIL standards, the DoD standards, which are supposed to be protecting. So who knows? You know, there's geopolitics, China, India, some other country. You know, it's a wild west out there right now in terms of the politics associated with the moon. But folks are getting geared up now, international law, looking at agreements.